And in this video, we'll continue looking at aldol reactions, but this time we'll begin by looking at crossed aldol reactions, which in the previous video we looked at aldol reactions between two molecules of the same aldehyde or ketone. In this video, we'll be looking at reactions between two different aldehydes or ketones. So I'll try to color code this. Hopefully it'll make a little more sense. But if we start with a mixture of this aldehyde, acetaldehyde in blue, plus propionaldehyde in red under basic conditions in water, then what do we get? We'll actually get 4 different products. And so the first product will be if we have 2 copies of the acetaldehyde, and I'll begin with the enolate to save time. But if the acetaldehyde enolate plus acetaldehyde react, then we'll get this aldol, which will dehydrate to form this condensation product. Reaction 2, or product 2, would be the same acetaldehyde enolate plus propionaldehyde we would get this aldol product, which would dehydrate to form this aldol condensate. With product 3, we'll use the propionaldehyde enolate plus acetaldehyde we would get because this methyl group here would be down here now, and that would dehydrate to form this condensate product. And finally, product 4, the propionaldehyde enolate reacts with propionaldehyde we would wind up with this aldol, which would dehydrate to form this condensate product. And so this mixture of 2 different aldehydes gives us 4 different products. And so it's not synthetically very useful to try this reaction. That we would get an equilibrium between 4 different products. Controlling which way the reaction goes would be next to impossible. You would have to find a good way to separate the 4 products from each other, and the yields would probably be really low, and so it's not a very useful reaction. But there are ways to take a cross-aldol reaction and make it controllable so that you can direct to one of the possible products. And we'll go over 3 ways in which that can be done. The first one is only one compound has alpha hydrogens. For 2, one compound has very acidic alpha hydrogens, and 3 directed aldol reaction using lithium diisopropylamine as our base. And so we'll go over all 3 of these methods. We'll start with number 1, where only one compound has alpha hydrogens. So if we react these 2 aldehydes, benzaldehyde, let me try to color code this again. Benzaldehyde plus acetaldehyde. This time we'll do this in acidic aqueous conditions. The aldol product will look like this. And it would dehydrate to this. In fact, this aldehyde is cinnamaldehyde, and it's found in cinnamon. But if we take a look at our starting materials, we'll notice that the benzaldehyde has no alpha protons. So it cannot form an enol. Whereas the acetaldehyde has 3 alpha protons, any one of which can be pulled off in order to form the enol. And so in reality, we would get this enol plus this aldehyde that react to form that aldol. And we avoid the reaction between acetaldehyde and acetaldehyde by slowly adding our acetaldehyde to the benzaldehyde solution. So we would start with a flask of benzaldehyde, and we would add the acetaldehyde dropwise, so that at any given time the acetaldehyde will be greatly outnumbered in solution by benzaldehyde, and so that we would favor this reaction between the acetaldehyde and benzaldehyde rather than acetaldehyde in itself. Now we can also do this when using an aldehyde and a ketone, because the ketone enolate will tend to only react with the aldehyde. Ketones do not appreciably self-condense, and this will be called a Claisen-Schmidt reaction. And again, that's ketone plus aldehyde. And so if we use benzaldehyde again, because it has no alpha protons and cannot form an enolate, and we'll use this ketone, this ethyl methyl ketone, and this time we'll do it under basic conditions. Then we'll get this aldol condensate forgot the methyl group. Because this species, the ketone will form the enolate, and that enolate will attack the aldehyde and forming the aldol, and then the aldol will dehydrate, forming our aldol condensate. So these are two ways, two examples where we use the strategy of using one compound that has alpha hydrogens, and that would be either the acetaldehyde or this ketone, because the other compound in our reaction has no alpha hydrogens. The next strategy that we'll discuss strategy 2, one compound has very acidic alpha hydrogens that in this case we'll use not benzaldehyde but this aldehyde, and this aldehyde does have an alpha proton, but our other compound will be this, where we have two alpha protons, and these alpha protons are much more acidic. And so this will form a more stable enolate that can better attack this aldehyde in red. And so the product of this reaction the dehydration product of this reaction, after we remove the hydroxyl group, will be this. This alpha, one of these alpha protons will be removed, and then we can form a stable enolate that can attack that aldehyde, forming an aldol. The aldol can be dehydrated to form this aldol condensate. And in this case, it's the conjugated system is a little larger, and so that should be more stable than some of the other ones we've seen. But anyway, that's strategy 2 with the very acidic alpha hydrogens. And if you should look for compounds like this with the two carbonyls beta to each other, because those alpha hydrogens in the middle will be particularly acidic. So strategy 3 is the directed aldol reaction. Using lithium diisopropylamine. And so when doing this reaction, we'll take one compound, react that compound with LDA at negative 78 Celsius, and that'll force that compound to form the enolate in 100% yield, and then we slowly add the second compound. So again, we'll start with acetaldehyde. The first reaction will be with LDA at negative 78 C, and that will force the acetaldehyde to the enolate in 100% yield, and then we slowly add our second aldehyde, in this case propione aldehyde. That will do that first, and then finally we'll do react that with acid and heat to force the dehydration. And so after the dehydration, we'll wind up with this aldol condensate. And again, the point of this step is to force dehydration. Now, because we are using LDA, we're going to get the kinetic enolate rather than the thermodynamic enolate. So if you remember that from the Chapter 18 videos, that different bases will favor different enolates when more than one enolate is possible. And so if we use a ketone, the methyl ethyl ketone, again, then there are two sets of alpha hydrogens now. But these alpha hydrogens on this methyl group are going to be easier for the LDA to pull off. And so it will favor these alpha hydrogens on the right. And will form this kinetic enolate in 100% yield. And then the next reaction will be with acetaldehyde, and that will form this aldol product. Nope. Yep. Yeah, because this is the methyl, and so let me label these somehow. We'll put a star, so that you know that this carbon becomes that carbon. So we flip this molecule around, and then with acid and heat we dehydrate. And we arrive at that aldol condensation product. So that's the third way that we can use a crossed aldol reaction, and in a practical manner. That we take one of our reagents, we react that with LDA to convert it to the enolate 100% yield, and then we slowly add the second reagent to that enolate solution in order to arrive at our desired desired product. And so here we've essentially switched. I should have paid more attention to my color coding and made this blue so it would match up above. But we can do the same thing with ketones. If we have more than one possible enolate, we'll form the kinetic enolate, and we can make the reaction work between ketones and aldehydes that way. So anyway, we can also do intramolecular aldol reactions, and these are a good way of forming 5 or 6 membered rings. And so if we start with a molecule like this, where we have both a ketone and an aldehyde, then we have 2 sets of alpha protons, this here and this, and these 2 here and these 2 here. But the aldehyde will be more reactive towards nucleophilic attack than the ketone. And so we want the ketone to act as our enolate so that it can attack the aldehyde as the nucleophile. And so if we do this reaction in basic conditions, then we can have a hydroxide ion, pull off one of these protons, kick the electrons up to that oxygen there, forming this enolate. The electrons can come back down, and those double bond electrons will attack that carbonyl on the aldehyde end, forcing the electrons to that oxygen. So now we've closed. This will form a ring between this alpha carbon and this carbonyl carbon. So that's a 1, 2, 3, 4, 5 membered ring. and we'll say that this is carbon 1, and 2, 3, 4, 5. So 2, 3, 4, 5. 5 would have our hydroxyl group. Carbon 1 have our ketone. Oh wait, we're in basic conditions, so that would be negatively charged. But we can still protonate this and once it's protonated, then we've got this proton here that another hydroxyl ion can attack. We can kick off that the hydroxide as an acceptable leaving group under basic conditions, and arrive at this product with the double bond and the ketone conjugated to each other. So when we have both an aldehyde and a ketone, the ketone will form the enolate and attack the aldehyde. Ketone to enolate, attack aldehyde. But if we have two ketones rather than a ketone and an aldehyde, then we have to look for the product that has the most stable ring structure. So now we have these two ketones, and so we react this, say, under basic conditions with water. Then we have two potential aldol products. If this ketone, let's label this A, label this B, and we have our two alpha proton, or two alpha carbons, well, actually more than two alpha carbons. Yeah, it's symmetrical. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 1, 2, 3. So we'll call this, I'll try color coding it, 1 and 2. And so it's because it's symmetrical. Essentially, we've got these two carbonyls are actually the same. I shouldn't have called them A and B. We've got alpha carbons 1 and 2, and on the other side we have alpha carbons 1 and 2 as well. So let's look at our two different possible aldol structures. If this alpha, if we form the enolate using carbon 1, then it would form a ring. It would attack this other carbonyl, we would form a 1, 2, 3, 4, 5-membered ring. So let's try to draw that. It carbon 1, 2, 3, 4, 5. So on 1, we would have this ethyl group. On carbon 2, you would have the ketone. Carbon 3, carbon 4, carbon 5 would have hydroxyl and a propyl group. The other potential product if carbon 2 were to attack the carbonyl, then we'd have a 1, 2, 3-membered ring. And we'll try drawing that out. Carbon 1, 2, 3. So carbon 1 would have this ketone group. Carbon 2, carbon 3. But this 3-membered ring is unstable. At least not stable when compared to the 5-membered ring. And so this 5-membered ring is going to be more favored, and so we'll produce this 5-membered aldol. And if we dehydrate by pulling off this alpha proton and kicking off this hydroxyl, then we'll wind up with this aldol condensate product. Whereas if we were to try dehydrating our 3-membered ring, we would wind up with this cyclopropene, which is very not stable. And so we're going to favor our 5-membered ring over our 3-membered ring. So when we're dealing with 2 ketones, look for the more stable ring. And we'll finish this video up with a synthesis example. So we want to convert this 6-membered ring with the 6-membered cyclic alkene to this alpha-beta unsaturated aldehyde. How do we go about doing that? Well, essentially, we need to convert this to a pair of aldehydes and then do an aldol reaction between those aldehydes. So the way we can convert an alkene to a pair of aldehydes is 1, react with ozone, and 2, react with zinc. in acetic acid, and that will form this pair of aldehydes. Let me make sure I've got my numbers of carbons correct. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So I think I've got the number of carbons correct. And then once we have this, we can use either basic or acidic conditions. Let's say acidic conditions. One of these will form an enol. And once we have the enol on one of these aldehydes, that enol will attack the other aldehyde, forming our 5-membered ring with this aldehyde. The aldol would have a hydroxyl group here, and then we dehydrate the aldol to form this aldol condensate product. So that's it for this video on crossed aldol reactions.